Question 3. Nitrogen is generally an unreactive molecule, but it does react under certain conditions. Part A. Give 2 reasons to explain the lack of reactivity of nitrogen. So nitrogen, first of all, has this triple bond. Very strong bond. So we shall say it has a strong triple bond. A strong triple bond. And on top of that, this nitrogen is electronegative. So both of them are electronegative. They tend to pull the bonding electrons towards themselves. So the polarity here disappears. Okay? The dipoles here will disappear, and that therefore means it is going to be nonpolar. So something that is nonpolar, you have to use harsher conditions to cause it to react. So the other reason is that it is non-polar. Then part B, they are saying nitrogen can react with oxygen in an internal combustion engine to form a mixture of nitrogen monoxide and nitrogen dioxide. Figure 3.1 shows a reaction scheme involving nitrogen. So reaction 1, we are seeing nitrogen reacting with oxygen to give us these. Then what is produced here now reacts with water to give us a product. And then the nitrogen dioxide reacts with unburnt hydrocarbons to give us PAN. This is a main component in photochemical smog. Okay? It is very deadly for those that are asthmatic. Okay. Now, write an equation to show the formation of a mixture of these two. All right, so we have nitrogen here. It is going to react with oxygen, not so? Then to give us the mixture of these two, I will just write nitrogen monoxide, then plus nitrogen dioxide. Now, nitrogen's 1, 1, then this one 2. Nitrogen is balanced. How about oxygen? Oxygen is 2 plus 1, that is 3. Now, for me to get a 3 here, I will put 3 over 2, because you get 3 over 2, then times this 2 that is here. So they cancel out, and then you get that 3. You see that? All right, let's continue. Roman 2. Give the formulae of products of reaction 2. Now, nitrogen dioxide plus water, you can get nitric acid or nitrous acid. Okay? So they are saying formulae of compounds. So I can put nitrous acid, which is this one here, and then nitric acid. Write it like this. Then Roman 3, set one environmental consequence of reaction 3, this one here. I already said it that this is the major component of photochemical smog. So there is production of photochemical smog. I will just put photochemical smog. Part C, the Haber process involves the reaction of nitrogen and hydrogen to form ammonia. A catalyst is used which allows the process to be carried out at a lower temperature and pressure. Okay. Then we have this one here, the reaction, and it is exothermic. Okay. Because this one is negative. The enthalpy change. Use the information in C to complete the table 3.1. Now, when we look at what is here, enthalpy change of formation of nitrogen, since this is an element, enthalpy change of formation of an element is always 0. So we shall have 0 and then 0 here. Okay? Let me even note it here. Enthalpy change of formation of an element is 0. Now, the enthalpy change of formation of ammonia here. First of all, enthalpy change of formation, we are looking at formation of 1 mole of a compound. But what is formed here is 2 moles of a compound. Do you see that? 2 moles of ammonia. So that means for 1 mole, then I'll get the enthalpy change and then I divide it by 2. So since the enthalpy change of formation of these ones is 0, then the enthalpy change of formation of this one is what we are getting actually here. So you just divide that by 2. So we shall get negative 92 divided by 2, and the answer becomes negative 46 kilojoules per mole. Roman 2. Explain how the presence of a catalyst affects the reaction. This one increases the rate of a reaction. Okay? It increases the rate of the reaction. But they said explain how it increases the rate of the reaction, but how? So by providing a pathway, by providing an alternative pathway with a lower activation energy. The catalyst does not lower the activation energy of a reaction. It just provides a pathway with lower activation energy. Then, Roman 3, state and explain the effect, if any, on the rate of the Haber process as the pressure is lowered. So things to do with pressure, you have to look at gaseous compounds in there. All of them are gaseous. Now, this is one thing you need to know, is that using Boyle's law, pressure is inversely proportional to volume. Okay? So if you lower the pressure, that means the volume has to increase. And volume is directly proportional to the number of moles. So if you have many gas moles, then that means you are having a bigger volume there. You get it? Okay. Now, when we decrease the pressure, first of all here, the total number of gas moles, we are seeing 1 here plus the 3, that will be a 4. But then this other side, we are seeing 2. Now, when you increase the pressure, let me first say this one here. When you increase the pressure, then the volume is going to reduce. That means the side with more gas moles, it is going to react such that it goes, the equilibrium position is going to shift to the right with fewer gas moles, because you have increased the pressure, volume has to reduce. So where do we see less gas moles? On the right. You see that? So if you increase the pressure, then you get more yield. So it will go to the right. But then they said, when you decrease the pressure. So when you decrease the pressure, that means you are going to have much volume. Okay? So meaning the equilibrium is going to shift to the left, where we are having more gas moles. Remember, V is proportional to N. Is that clear? All right. So that therefore means that the rate of reaction is going to decrease. Explain. They said state. Let me go back to this. State and explain the effect, if any, on the rate of the Haber process as the pressure is lowered. Remember, the rate of that reaction is to give you the big yield. You get it? But now, since the position of equilibrium shifts to the left, so the process is lowered. You see that the process is slowed down. So I will say that rate of reaction decreases or will be lowered. Okay, will be lowered. Why? There will be few gas molecules per unit volume. Therefore, the number Therefore, the number of successful collisions, because remember, when you're talking about the rate, you have to talk about the successful collisions. It has to be in terms of the collision theory. So the number of successful collisions to give you the product will reduce. You see that? Reduces. So that is that. Part D. This molecule here has a double covalent bond between its nitrogen atoms. This consists of a sigma and a pi bond. Roman 1. Complete this figure 3.2 to show the dot and cross diagram for the nitrogen fluoride. Okay? And then, in fact, it is nitrogen. Is it perfluoride? Whatever the case. Show outer electrons only. Now, we know that fluorine is from group 17, so it has 7 electrons in the outermost shell. It is going to, you have something like this. Nitrogen must have 3 bonds, okay? So nitrogen, there are 2 of them. Then we can have a fluorine here and a fluorine there. But now nitrogen must have 3. So if it is the 3, these are 2, we must have a third one, which is here. And they say this consists of a sigma bond and a pi bond. So wherever you see a double bond, there is one sigma bond, and then the sideway overlap. That leads to the formation of the pi bond. So we shall have, if I take the cross for the nitrogen, then the dot for the chlorine, I'll get, fluorine is supposed to have 7. So this is 1, then 2, 3, then 4, 5, then 6, and then 7. Okay? Then also here I'll have a cross and then a dot. Then this will be 2, 3, 4, 5, 6, and then 7. Now for nitrogen, nitrogen has how many electrons in the outermost? There are 5, because it is in group 15. So if there are 5, then we are going to have, already this one is 1. Now there is a double bond here. So one nitrogen has this, another one has this one. Okay, let's count the 5, okay? Let me repeat this one. There is 1 here. This is a second one, okay? This is a third one. Then we must have a 4th one here and a 5th. The same to this one, okay? 1, 2, 3, 4, 5, okay? But now they are sharing, okay? So if they are sharing, then I need to put one here and then another one here. So there is a pair and then a pair there. So that is how it is going to be. Put a pair here and then there. Deduce the hybridization of nitrogen, of the nitrogen atoms. So the hybridization, since this is a double bond is sp2. So you don't need to waste time. That is sp2. Okay. A triple bond is sp. Let me just write here. Single bond is sp3. Double bond sp2, and then triple bond. The triple bond is sp. Roman 3, draw a diagram of pi bond between nitrogen atoms in this molecule and describe how it forms. Of course, usually in 2D, we have, there is a sigma bond. Actually, it's something, it is like this. You have the P here, there is this one here, and then this one here. So this is head-on overlap, then they form the sigma bond, okay? That is a sigma bond. then these two sideway overlap. So this one is going to bend with this one here, then they form a ball. So the electrons can move from here in both, from this side to this other side. So there's a nitrogen here and then a nitrogen here. So it forms a bond. Now, in books, they usually represent it like this. So they put a curve just like that above and then below that sigma bond. So that is how it is. So this is the one you're supposed to draw. That one there. And then they say that explain, describe how it forms. So here we say the pi bond, okay, is formed by sideway overlap of the p orbitals. So I can say 2p because nitrogen will have 2p orbitals above. So they overlap above and below the plane. That's why we have put this one here and then this one down here.